Assalamualaikum and a very good morning. So, firstly, our project investigates the structural performance of an EV battery tray using finite element analysis. The battery tray must support the battery pack while protecting it from operational loads, vibrations, and impact from road debris such as rocks and chipping. The objective of this project is to evaluate the stress distribution and deformation of the tray under loading conditions to ensure the design is safe, durable, and capable of protecting the battery system during vehicle operation.
For this project, we have five objectives. First, to design and purpose and improve EV battery pack tray and multi-system that maximize battery protection against structural and impact damage. Second, complies richly with international automotive standard. Third, to ensure the system is lightweight and easy to maneuver. Fourth, align the material life cycle and design philosophy with the UN Sustainable Development Goals (SDG), which is SDG 9. And five, to integrate specialized thermal barrier, crash protection zone, and fine retardant shielding directly into the lower tray assembly to isolate battery cell and prevent thermal runaway propagation.
Hello. So for our pre-processing, we design our EV car battery tray. We were using the SolidWorks. So as you can see, this is our EV car battery tray, which has 1, 2, 3, 4, 5, 6, 7, 8 support on each side. And then um, this is our boundary conditions where the battery tray is supported with eight L-shaped brackets where we put it as a fixed support. Okay, so for the material properties, we're gonna use aluminum 6061 alloy where the yield strength is 5.51 times 10 to the power of 7 Newton per meter square. And then for the tensile strength, it's about 1.24 times to the 10 to the power of 8 Newton per meter square. For the motor type, it's going to be linear elastic isotropic, which means that the stress is directly proportional to strain and the material will completely return to its original shape. Last but not least, the default failure equation, we're going to use Max von Mises stress.
As you can see here, our group is using a triangular mesh generation for our design. And from our simulation, our group managed to obtain the information for our mesh generation. Prior to the simulation, our group decided to apply three different forces at three different areas, as you can see in the slide.
To validate our FAA model, we perform manual calculation by simplifying the tray cross member into standard beam element under a 2 Newton per millimeter load. We compared two critical profile under fit boundary condition, section A at 1500 mm and section B at 1100 mm. The calculation revealed that increased the span length by 36% caused a massive drop in structural stiffness. As a direct result, the elongate member in section A experienced a significant downward deflection of negative 6.957 mm, while the shorter section B safely stripped its displacement to just negative 2.012 mm. This manual analysis directly justifies our final SolidWorks design. Since long unsupported spans are vulnerable to axis reflexing, we integrate rigid internal partition ribs. These ribs break long span into smaller, high-stiffness compartments that mirror section B, successfully distributing the heavy payload, controlling global deformation, and maximizing structural safety.
Now I will be walking you through the static analysis of our 6061 alloy molded tray. Starting with our post-processing result, as you can see, the resultant displacement is extremely minimal, reaching a maximum of only 0.4915 millimeters under load. Next, looking at the von Mises stress in this image, our simulation recorded a maximum stress of 36,000 kilopascals. The critical red-orange section is concentrated around the bracket hole, while the green areas appears at the side of the tray. Most importantly, this peak stress remains comfortably below the material's yield strength. Finally, this image illustrates our design safety factor. We successfully achieved a minimum factor of safety of 1.532. This confirms that the tray will safely withstand the applied normal forces without any risk of structural failure.
To conclude, our proposed EV battery tray successfully meet all core objectives. It effectively mitigates structural failure and fire hazard on rough road, directly reducing potential repair costs. Our FEA validates that the mounting system is structurally sound, offering superior battery protection. Lastly, the integration of lightweight materials justify our project scope, adhering to international safety standards while promoting sustainable automotive manufacturing under the UN SDGs. Thank you.